All right, so in this part of class, my goal is to have us figure out the math behind both this diffraction, that's when the light is bending through the slits, and interference, that's the pattern of bright and dark spots that comes up from it. Right? So this particular pattern depends on three things. It depends on the wavelength of light. That symbol is lambda. You've seen that one before. This pattern depends on D. D is the spacing between the two sources. When I do this for light, I need a really small distance between the sources, or else the waves don't interfere. So D is distance between sources. One that you can't actually switch in your simulations very easily is going to be L. L is also going to be a distance, and it's going to be a distance between the source. How about we do the distance between the slits and the screen that's showing the bright and dark spots? Those three things put together are going to give us our spacing. Y is the spacing between bright and dark spots. How about we say a spacing between, we'll just do the bright spots. So we've got all our symbols. Please notice at this point, all of the units are what?
Distance.
Distance. So I'm measuring them in?
Centimeters.
Close.
Meters.
Meters.
There we go.
Mathematically, nice. I got to change this all to meters. All right, so I got to change this all to meters when I do it. Okay, so from here, now let's look at our picture, right? So let's say I have my laser beam, right? And my laser beam is putting out monochromatic light, meaning one wavelength, one color, right? Let's say my laser beam is putting out light, all one wavelength, and then it hits two openings. All right, something that looks like this. D is going to be this distance between the two openings. And this makes a pattern of bright and dark spots on some nearby screen. Remember that unless I have like a fog machine, I can't see the beams of light. All I can see is when they hit some other object in its path and make bright and dark spots. So this is my screen. And it's the thing that the light is going to reflect off of so that I can see it with my puny human eyes. Now, let's say it's a nice red wavelength, nice and easy to see. That red wavelength is going to make a bright red spot in the center. That one has a special name just because it's the one in the center. It's called the central maximum. It's the bright center spot. But evenly spaced going out on all sides, I'm going to have smaller other spots. I'm going to try to draw them evenly spaced, but you'll live if they're not perfect. Those are called the first or second or third order maximum. One other thing that you're not going to necessarily see in the simulation is what these numbers are. We call this M. M is order number. It's some integer number telling you a distance. So for instance, this one in the center, this is my most center maximum. That's M equals 0. On either side, I have M equals 1. That's my first order maximum. M equals 2. It's just telling you like which dot is it away from the center. 3. This is M equals 1 again, because it's adjacent to the center. M equals 2 down here. Right? So what we can't see without a fog machine, what we can't see is this actually makes beams of light that kind of spread out like this. Nice evenly spaced rays of constructive interference. that we call the antinodal lines, because that's where it is bright. Antinodal lines are where crests are meeting up with crests and troughs are meeting up with troughs, so that we get constructive interference and we see bright light. All right, so let's see. This picture has lambda, it has D, it has M. How about we give it L? L is the distance from the screen on the left to where you have the double slits, right? And finally, Y. Y, where we call the spacing between bright spots. Y, go from the center maximum to some nearby bright spot. So this would be Y. Okay, so then, math equation for this, you're only ever going to need to solve it for Y, right? Y depends on M, the order number. If it's farther away from the center, then the spacing is bigger, right? If I did M to the third maximum, then I would use M equals 3, right? Because it's farther away. So it depends on M. If I choose a later order number, then it's farther from the center. It depends on wavelength. The bigger the wavelength, the more spread out it is. That's why red's on the outside and violet's on the inside. It depends on L. How far is it away from the screen? Oh, and the thing you guys might have got from your lab already is that D is inversely related. D is inversely related. When you do Y versus D as a graph, it's that like decreasing graph asymptotically approaching 0. Now, that equation's not horribly difficult to work with. The only thing that's going to be horribly difficult about it is that the units are almost never in meters. You always have to change it to meters. So for this, let me switch over to the big screen. I've got one written out already. I did for this assignment put on the back page your conversions to meters from everything else, just in case you need it. All right, so here's an example of where this gets used for. Okay. Scientists that study crystals can't really just zoom in and see things that are as small as atoms. In order to see them, you need wavelengths that are approximately the same size as the thing you're studying, right? The problem with crystals is they're so darn small that you can't use normal light waves. You actually can't zoom in with a visible microscope far enough because the wavelengths of light are so big compared to the size of the crystal you're looking at, right? So with X-ray crystallography, what they do is they take an X-ray and it has a wavelength of 0.1 nanometers. So maybe if I'm like doing this as a homework problem, I like highlight the 0.1. That's my wavelength. So that's going to be lambda. And it casts bright spots of X-rays spaced 16.7 centimeters apart. Since it's talking about the spacing between bright spots, I know we're talking about Y. So I have lambda, I have Y, and the distance between the photographic plate is 0.5 meters. That's L. Where's the screen? How far are the lights spaced apart? What's the wavelength? Then a scientist could study this backwards and find how close are those atoms together. This is how we figure out crystal structure of things that we can't just zoom in and see with a microscope. Okay. So first, I would take lambda, change nanometers to meters. Take centimeters to meters for Y. Take, oh, that's already in meters. No conversion necessary. In this case, I want adjacent atoms. So think to yourself, I want the first order magnitude. I want the first one, the one that's right next to the center. So when I go calculate this, I needed to do a conversion factor. And in case you haven't done them in a while or never actually learned them, what I would do is take the N for nanometers
and replace it with its conversion factor. So the number zero point 0.1 stays the same, but I multiply it by the conversion factor of 10 to the negative 9. The 16.7 stays the same, but I multiply it by 10 to the negative 2 to change it from centimeters to meters. Finally, I grab that equation, right? So y, that's the spacing between the bright spots. That was my 16.7 centimeters. I take my lambda, that's the wavelength of X-ray, L, the distance to the screen, and since I want adjacent bright spots, the ones that are just exactly next to each other, that's why I chose m equals 1. Finally, I use that to solve for d. D ends up being 3 times 10 to the negative 10th meters. We couldn't have possibly used light, regular visible light, to do this because regular visible light is bigger than the atoms they're trying to see, right? It's bigger than the structure that they're looking at.